So I want to talk about this Windows project here, ED308. This is the main one. Just like I said, ED202 is the most essential part on Linux, where you do the straight up basic buffer overflow and learn how to do it. This is the equivalent on Windows, and it's quite a bit longer and quite a bit more complicated, but it is essentially the same thing as 202. So you go on, first you have to, by the way, and here I did it with cloud machines, a Google Cloud server and a Google Cloud Debian machine, and you can also do it with local machines, which is how I'm doing it now with the VM version here, which I just updated today, but it doesn't really matter. They're very similar, and you could use any version of Linux, but I wrote this for Debian because I've gotten pretty fed up with Kali Linux, which is what I used to use because they keep breaking everything. Anyway, so one thing you have to do is go into performance options in advanced system settings, control panel system, advanced system settings, and make sure data execution prevention is set to this setting. Otherwise, it'll break this project. And client machines like Windows 7 and Windows 10 are this way by default. Server machines are the other way by default. So if you're running a server version, you'll have to change it and then restart your machine. So then, I'm using Windows 10 this time. I'm using the Flare VM, but you could use any version of Windows. And so I downloaded and unzipped the Vulnserver, and here it is. And you can see this program has two pieces. It has vulnserver.exe and it has essfunc.dil. So the developer compiled their product twice into two pieces, an exe and a dil. No, City College doesn't have any free Windows anymore. But if you look at these projects, you can get free trial versions of Windows. It's in the projects where you set up the machines, and by the way, it's also on my homepage. If you go here, I guess I put it at the bottom. You can get Windows, Microsoft evaluation software here. This is what you can get, Windows 10 or Windows Server this way, and that's what I've been using for years. Very important. All right. Good. So I've got this IP address, 172.16.123.14, and I've got this little program running, so I can run this program, and now it's listening for client connections, and I've got a Debian machine on the same network, and I've connected to it with SSH, so I can check to see if that works by, say, netcat 172. I want that address, which is there. Okay. I connect to it 172.16.123.14 and port 9999, and there it is, vulnerable server. So help will show you that it has various functions. These are to look sort of like an email server, just various functions. Each ones have different vulnerabilities, and the one we're going to attack is trun, which has a simple buffer overflow vulnerability. And so I can execute trun, and then I can give it a value like .aaa, and it will then say trun complete, which means it ran without crashing. And I'm going to exit. So now I'm done, and now this is going to close. All right, so this is the server running to handle client responses. And now we want to crash it with a fuzzer. So let me get back to the project here. All right, so you run it to make sure you got the networking correct and such, and the firewall turned off and all that jazz. And now you can make a fuzzer in Python, where it asks for the length of an attack, and then it prints trun space dot and then a bunch of A's. So I've got that fuzzer here. All right, ls, and I can make this bigger. All right, so the fuzzer is vs fuzz1. So I can run vs fuzz1. All right, and now let's bring up the Windows machine in the background so we can see what it does. So here's the thing running, and if I give it 2000 A's, it crashes. And it might give me a box showing me an error message, or it might not. But anyway, that was a crash. So it crashes at 2000, and that's a thing to know. So now I'd like to know more about it. So just like we did on Linux, I put it in a debugger so I can see why it crashed. So I installed Immunity. I run Immunity, and then I go File, Open, and I open Vulnserver, which is here because I've opened it before. And so it loads it. So here you see the assembly code instructions. Here's the registers. Here's the stack. And here's just a place where you can dump addresses. And it is not running. It's paused right now. So I start it with the run button here. And now it's running. And by the way, it's opened a window over here. You can see the typical window showing it's running. So now that it's listening, now I can send that fuzz attack again. So I run it again, give it 2000 again, and it crashes. And now I can see, now I sent it 2000 capital A's, and notice at the bottom it tells you where it crashed. Access violation when writing to 41414141. So it tried to write to an address that was 4 capital A's. So some of those letters I typed in turned into an address controlling a write operation. And as we did in heap exploits in Linux, you can take over a box with a write operation. You just have to write to an address that will eventually find its way into the EIP. So that's one possible attack, but I want to do a much simpler one tonight. So I do debug, restart, and yes. And then it's run it again. So now it's ready to attack again, and I'm going to send 3000. All right, and now it crashes again, but this time its access violation when executing 41414141. So now some of the letters I sent in found their way directly into the instruction pointer. So this is the simplest kind of buffer overflow, which is what I want to do, where you can directly feed in data that will affect the instruction pointer. Okay, so now I need to send a pattern of characters to find the so that's the crash. I want to make a non-repeating pattern, and so that is this thing. I wrote some people use a Metasploit module that makes a non-repeating pattern. I just wrote a Python script that will just count from 0 to 5 and then count from 0 to 10 twice and then just print 3 digits and an A. So it makes 000A, 001A, 002A. You could do anything, but that's some way to, and this is a total of 10, 100, 500 times 4, 2,000 characters. So I want to have a 3,000 character attack, so I'm going to send 1,000 capital A's and then that pattern of 2,000 characters. And that's what this thing called VSEIP does. It sends that pattern of 3,000 characters to the server. So let me just make this smaller so I can easily reach behind it. I restart the server again and make sure and run it again so it's listening. And then I run that program, which let's just take a look. I think it's VSEIP1. Let's cat VSEIP1. And yeah, that's it. Here's the pattern of repeating characters. So I run that one. It sends it, it crashes, and now it crashed at 35324131. That's the address where it crashed. And so that tells me where it is. That pattern, 35324131, if you turn them from hex back into letters, that's 52A1. So that is here. It's backwards, 52A1. So it's about halfway through, so I can now figure out how many characters in that is, and that is 1006 in, plus the first 1,000. So now I know how to hit the instruction pointer. 2006 bytes. The next 4 bytes will go in the instruction pointer, and then you have to add more characters after it to keep the total length at 3,000, because we talked about it before. We now know that a 2,000 byte attack will have a different crash than a 3,000 byte attack, so I want to never change that link to make sure I continue crashing at the right code. So now here's the code that does that. 2006 A's just to get to the right place, then BCDE to hit the instruction pointer, just to be something I can recognize when I hit it, and then enough F's afterwards to just make the total length 3,000. So that thing is VSEIP2. So I do debug restart and run it again, and then I run VSEIP2. And now I get 45, 44, 43, 42, or B, C, D, E. So it worked. The instruction pointer is right where I think it is. So now I control the instruction pointer. All right. That's not enough to win yet, though. Let's go back to here. Okay. So now I need to figure out how to put in my exploit code somewhere. And Windows has address space layout randomization in there. But notice something. Here's what I fed in. Trun AAAA, this is what I put in. And I know there'd be like 1,000 of these. Here's a bunch of Fs. Notice that, pointed to by ESP. So if I click on ESP and then right-click and follow in dump, I can see all these Fs. And notice, so some of the Fs, remember I put in about 2006 A's, then BCDE, then almost 1,000 Fs. That was my attack. So some of those Fs are right here in the stack. And if I scroll up a little bit, I'll see it's the first F right there in the stack. So I just injected all these A's. This is the instruction pointer. That F right there is the next character. So I control that stuff. So I can put code right here, and it will be right at ESP. This is important because remember the code is randomized. I don't know what any absolute addresses are. But if I can put an address here that points to a jump ESP, then it will trampoline off the jump ESP and find my attack code wherever it is and run it. This is the simplest case of return-oriented programming. So if I can find code that is not randomized in memory, that contains a jump ESP instruction, and put that address here, I can redirect execution to this even though I don't know where it is. And then I can take over the box. And that's what we're going to do. So one thing we need to do is test for bad characters. So it is C code, like always, so null bytes will terminate it, and you might expect things like line feeds and carriage returns and spaces to terminate it. But it turns out in this case, the only thing that matters is the null byte. And you go through a test, which I don't think I'll bother here testing it. I think I'll just get to the end point is bad char 2. Bad char 2 takes from 1 to 256 and prints them all. And it doesn't fit the last character. So this is going to give me all the characters from 1 to 255 and inject them. And then it's going to make the total length 3000 again. So it's going to put those in right after all those Fs went. So let's just try this one, bad char 2. Debug, restart, and run the program again. And then bad char 2, which is vs bad char 2. Okay, so now it hits. It crashes when executing 45, 44, 43, 42, so it did the same thing. Here is the stack pointer. So if I right-click and follow in dump, I will see here's the A's and the ABCD. Here it is, 01, 02, 03, 09. These are all the numbers counting up. And if any of them was to terminate the string, it would stop. And I can see that they all went in right up to FF. So there are no more bad characters. If anything like space or tab or anything terminated the string, it would stop inserting after that. So now I know I can use 255 of the 256 possible bytes in my attack, and they will be transmitted successfully to the target. So that's one good thing. So now I can make so now I need to find my trampoline point, and for that I need Mona. And this is why I had to use immunity instead of OllyDebug. As far as I know, you cannot do this in OllyDebug. But immunity lets you add Python code, and Corlance Coder wrote this thing, which is great, this tool called Mona. You download it from GitHub, and then you move it into the right folder, which is this Program Files 86 Immunity Debugger PyCommands, where it has other ones. You add it there. So Mona is one of the effective PyCommands, which I've already done, and now I can run Mona modules. So let's do debug, restart, and yes, and I'm not going to run it yet. Now I can do bang Mona modules. And what this does is it shows you the modules that are loaded to run this program. And it tells you what security features are turned on. Here's rebasing, we just talked about in a lecture, which moves DILs to their unexpected address. Here's a really important one to us, ASLR, Address Space Layout Randomization. And here's non-executable. So this ASLR would mean that we can't tell what address that module is. It's going to move every time the process is relaunched. And NX would mean I can't execute code there. Well, all these are executable. So an ASLR is turned on for all of them except two, and those two are Vulnserver itself and ESS Func. So the program that was written here was compiled without the switch turned on that would make that stuff executable, which is common for old programs compiled for earlier versions of Windows. The rest of this stuff is Windows internal libraries, and all those are randomizing. So if I was to try to attack Vulnserver itself, though, notice that it's always at 400,000, like any executable, and therefore all the addresses in this module start with 00. And therefore they all contain that null byte, so they're going to break my attack. So I can't use this module. But ESS Func loads at 625000, so most of the addresses in there are not going to contain null bytes. So all I need to do is find a jump ESP here. And that turns out to be pretty easy to do because there's another monomodule here. You can, if you're using Kali, you can use this thing called NASM shell to find it. If not, then you'd have to just look in a manual. But a jump ESP is FFE4. And there are some other ways to do it too. You could have a pop ESP followed by return, which would accomplish the same thing. But it turns out that a jump ESP is something we can find. And you find it this way. Bang Mona find this series of bytes, FFE4, in that module. That's all you have to do, which is why this is wonderful. So I have to execute that in Mona down here. And it will quickly go through and find that there are something like 8 or 10 of those in that module. And they're all perfectly fine. All I have to do is jump to any of these addresses. The address will not be randomized, and that will jump back to the stack and hit my Fs, where I can put in whatever I want. So I might as well just use the first one, 6250 11AF. The only reason I would avoid one of these is if there was a null byte in the address, and that's never true. So now I can improve my module. So I have 2006 A's. Then I put in that address backwards, 6250 11AF, so it'll hit the trampoline and come back. Now I can put in, after that, I put in my exploit. And I'm going to put in a fake exploit just to test it, a NOP sled, and then some breaks, and then padding. So the NOP sled will be 16 no operations, and then a CC, which is an int3 break instruction, which will go back to the debugger, and then enough Fs to pad it to 3000. And the reason I do this is I'm going to test to make sure this works. Can I bounce off the trampoline and hit the NOPs? And can I execute the NOPs and get down to the break? Two things might go wrong. If that module is randomized or this address is wrong, I won't make it back to the stack. And if the stack is not executable, then I will not be able to execute these NOP instructions and I won't make it down to the break. And that's what turning off data execution prevention did in the very first step right at the beginning, where I said you have to turn that off for this exploit to work. So this thing is VSEIP3. So I can go back to the CPU menu window where you normally go and then run this. And then I can send VSEIP3 and you see it hit the int3 command. This is what I wanted. And you see here I am with a bunch of Fs. That's what these 46s are. If I scroll up and see where I was, there we are. There's the NOPs. Here's that address, 6250 11AF. Here's the A's. This is what I injected. Then are the NOPs. It did NOP, int. So it worked. It made it to the trampoline. It bounced back to the stack. It executed code on the stack, and it hit the interrupt. So I know everything is fine. And now all I have to do is put real attack code instead of that stuff. So all you have to do is, as we've always done, make it in Metasploit. MSF Venom can be used to make exploit code. You have to put in the command and control server IP address here, which is going to be your Linux box, and then it'll start listening on port 443. So you can make a working exploit, and I had one here. Let me get out of this, and I have to run this stuff. You have to use sudo for MSF console, by the way. This is something a student was having trouble with last time. If you're not running Kali as root all the time, then you have to have sudo to listen on port 443. So I do that. Then I just use multi-handler and tell it which payload I'm listening for. And it will start listening on port 443 on my command and control server. And now I'm going to just run the program I'm attacking. I don't need to use the debugger anymore. I can just run it directly in the operating system. So I go to Downloads, Vulnserver, okay. And now I'll just run my attack from here, say. Just make it so I can see things here. All right, so if I do ls, that's VS shell, I think. Yeah, so let's move it all the way out of the way. So /VS shell. Oh, let's take a look at VS shell. Okay, so this is just connecting to the server. Here's that address, 6250.11af. Here's a 16-byte NOP sled, which I always put before a Metasploit payload because it often needs it. Here's the stuff that Metasploit wrote for me. MSF Venom wrote this thing. And then I put enough Fs at the end to make it total length 3000 and just send it to the server. So I run that one. And as you see, it works. It opened a interpreter shell. So I can now do things to that server like sysinfo to see that I'm a Windows box, and I can do all sorts of fun things now. So that's now I own that box, and that's what I wanted to show you. This is the essence, and all we're going to do is minor variations on this for all the future Windows exploits. This is the original plain old buffer overflow overcoming most modern Windows defenses. All right, so I'm going to stop that one.